This video shows how to analyze a composite structure by using flexibility method, or commonly known as force method. In this video, we will learn how to determine the redundant force of composite structure by using flexibility method. This is a composite structure where the frame ABC is fixed at A and connected to a 2-meter long strut CD. Axial rigidity EA and flexural rigidity EI from the frame and struts are given. In this video, I will present on how to determine the axial force of the strut by using flexibility method. Since the degree of indeterminacy of the structure is equal to 1, in this case, we could take strut CD as redundant. You can visit my other video on how to determine the degree of indeterminacy for composite structure by clicking the provided link. Generally, we need to analyze primary structure and redundant structure. If you are a beginner to the method, you may also visit my other video on how to draw primary and redundant structures in flexibility method. In this case, NCD is identified as redundant. Therefore, it was removed in the primary structure. And it was applied back as 1 unit force in redundant structure. We assume the NCD is tension in this case. It is also to note that there is no real load in the redundant structure. To analyze the primary structure, we can cut into 2 sections, one at CB and another at BA. This is the free body diagram for section CB with the range 1 to 2.5 meter. And the bending equation Mx is equal to 0 as there is no load acting on the section. This is the free body diagram for section BA with a range 0 to 3 meter. And the bending equation Mx is equal to 150 kilonewton meter. We can now analyze for the redundant structure. For section CB, the applied force 1 kilonewton can be resolved in X and Y direction to get the bending equation. Only the load square root 3 over 2 contribute to the equation. Therefore, Mx is equal to square root 3 divided by 2 multiplied with X. For section BA, both the loading at C contribute to the bending equation. We get Mx is equal to 2.5 multiplied square root 3 divided by 2 minus 0.5x. We can put all the internal forces in the tabular form. In this table, we list the inputs for the compatibility equations, such as the axial and flexural rigidity, the range of the section, internal forces such as bending equation M0 and M1, and axial forces N0 and N1. Then we can write series of compatibility equation. Equation 1 shows the compatibility equation for structure with one redundant. And it can be further expanded as in expressions 2 to 4. It is to note that the delta 10, 1, 0 and delta 1, 1 involve both moment and axial forces in solving composite structures. This is how we write for delta 1 naught as in equation 3. First, we insert bending information for section BC and BA. For example, for section CB, we insert the equation M0 multiply M1, the flexural rigidity and the range of the section. For example, for section CB, for the integration formula, we insert the equation M0 multiply M1, the flexural rigidity and the range of the section. It is to note that unless the axial deformation is stated to be ignored in the problem, it is common for beams and frames. If not, we need to include axial information for all the sections exhibit axial forces. In this case, the frame and truss. For example, for member CB, this is how you can insert the details in the formula. The N0 and N1, the axial rigidity, and the cross-sectional area. We need to then sum up all the flexural and axial deformation from all the members. Delta 11 can be calculated based on equation 4, which the details are solely from redundant structures. Then, by gathering the results of delta 10 and delta 11, we can solve for the compatibility equation. It is to note that delta 1 is displacement at the direction of the redundant force. It is normally dealt with support displacements at the corresponding redundant. Since there is no support displacement in this case, delta 1 is 0. And solution to R1 means solving for NCD for the real structure. As our earlier assumption, the NCD is in tension, when magnitude of R1 is negative, the real NCD is in compression. Once we have solved for the redundant force, we can determine the remaining outputs such as support reaction and internal forces by just using the equilibrium equations. We can also use the shown equations to solve for the bending moments and axial force. It can be used for support reactions too. For example, to get the bending equation for section CB, we use M0 plus M1 multiplied with R1. We can also determine the bending moment at specific point by substitute the value of X. Say at B, X is equal to 2.5. We can substitute X equal to 2.5 into the bending equations, negative 7.58X, and we can get MB is equal to negative 18.95 kilonewton meter. We then can draw axial force diagram and bending moment diagram from the analysis outputs we have determined earlier. Here, I have provided some scenarios for you to think about. You may need to find relevant equations for some of the above cases. What if you need to solve for support reactions in this case? What if there is a hinge near B at member BA? What if the support D has support settlements? What if members of structures have subjected to fabrication errors or temperature change? I hope you have understand the lesson well, and see you again in my next video.